Image enhancement. So this is where we don't necessarily need to change the data in the image. This is maybe something that's just done on the fly by the software you're using. But also, equally, it can be done you can create a new file, a new raster layer with the enhanced image. That may be a preference. So here we are going to be looking at some aerial photographs and just basically applying some enhancements to them to see what they might do and looking at the background of these things. So what do we mean? Well, generally speaking, we start by analyzing the histogram. The histogram is basically the distribution of values throughout the image. How often does a particular value occur? And here we can see we've got some, here I've said typically we're looking at values between 0 and 255, which is what's going to be visualized on the screen, but the data in the background here is from a remote sensing image. We can see down here we've got 13 bands of data. I believe this is Sentinel-2 data, although it should only be 12 bands because it doesn't matter, but when you receive the Sentinel-2 data, it actually looks like 13 bands. And the values there, they go up to a much higher value. They don't stop at 255, they go from 0 up to, can't quite remember, thousands anyway. This is why these extend beyond the 255, but the colors being shown on your screen are 0 to 255. That's also a limitation, something we have to work with. And how do we do that? Because if we have all these values going up to much higher values there, well, how are we going to get them into this 0 to 255 range? And what's important? Where are the relevant details? So in this histogram plot, we can see that we have lots and lots of cells, lots and lots of pixels actually in this case, in this area here. Very low values, interesting. And then there's a dip. And then we start getting information here. Well, obviously there's a lot happening here that we want to see. We've got lots and lots of pixels with information here. And maybe this is the most interesting area. So how do we get that? How do we get the program to focus on that bit of the image? That's what image enhancement is about, or what it can be about. So a simple method is called stretching. Now, typically, this is a word that comes from an older era in remote sensing, where our sensors captured data in 0 to 255 and the screens again 0 to 255, and typically from the camera, from whichever sensor it was, perhaps we didn't capture everything. There were no truly dark pixels and no truly bright pixels, so we had a data range that looked like this, or this was just the bit that we were interested in, and then we needed to stretch it out to cover the whole 255. So we maximize the range of values that we can see on the screen so that we can see nuances more clearly. That's why it's called stretching, because this has been stretched out. Now, if we think back to the previous slide, actually we're sort of more often now compressing things down so they fit in to this range, but that's another matter. But the terminology is still called stretching. So what we're doing, we just simply use this formula where the new value here is a function of the minimum. So we start from our 0 point, and then we look at the maximum and the minimum for the new values and the original values, and then to normalize this, and then we start counting from 0 and add on a normalized amount for each value. So this is sort of pixel, the new pixel value, that is each pixel that we're at. So we start counting from our new minimum, which in this case is going to be 0, and then add on to it the original value minus its distance from the original start point. That's that distance there. Let's say we're doing that particular one there, and then we are rescaling it using this. This is our rescaling factor. So that distance is rescaled to match our new scale. And then the new value, and then we carry on for each individual value, and we create this linear stretch. Histogram equalizing looks slightly different. And this is what might start off by looking a little scary. So this is the histogram value is the cumulative distribution function based on that. And what does that actually mean? Well, let's look at an example. So here I've created a very basic data set with some numbers, and here we have the value here and the number of pixels, cells with that corresponding value in this image. Not a very big image. So we have a number count. We have some cells here, some pixels with these different values. And we can see that the value 68 occurs 5 times within this image, within this raster. So what we're going to do now is we're going to add them up. So we go here and we start counting. We make a cumulative count. So we have one from the beginning. We start off with 1 cell there. That could have been another number. It's perhaps unfortunate that was 1. Maybe I was silly there. I should have started with some other number. This isn't the first. It just simply means that there's 1 value there in 52. And then we add the 3 from the next one. So that becomes 4. Then we add 2 to that. Then we add 3 to that. Then we add 1 to that. So this just increases all the time. Always increasing upwards till we get to the end there. And then we can see down here we need some parts with the CDF min, so we've calculated the CDF min down there, and we need the total as well, which is 64. So there are 64 cells here. Okay, so now the next step is to, as we can see here, subtract that minimum from the count, as it were. So we do that there in this column, and then that will give us the basic variant. This is a little inconsistent in how it's being shown, but we've actually then got this H3 value there by taking this number of new values minus 1, multiplying it with this, and that gives us our new range. And as we can see, it goes from 0 to 255. Nice. So instead of going from 52 to 154, they now go from 0 to 255. But we need to round these because we need integer values for this display, and so they get rounded down. So we can see here are the new values. So that's how we create the new values for our histogram. Good. And what does that do for us? Well, we end up with a slightly more even function, and in fact, we end up with essentially a straight line. So the grayscale value is here, going from 0 to 255 at the end there, and here we have the count. So we are going to increase all the way up in this straight line, so that we hop over values here just to maintain this straight line. So that's the histogram equalizing. And how do you do this? Well, you press the button. But this is what the computer's doing. This is how it's working. That hopefully helps to get a feel for what the histogram stretch might do. Is this always appropriate? No, it's not. We have several different enhancement methods here because they're not always appropriate. And when we get into standard deviation and Gaussian coming up now, we're going to see some very obvious areas where they might fall down. But they're definitely valid to apply. All of these can fail, or none of these are always appropriate. You have to choose the one that looks best. So standard deviation, how does standard deviation work? Well, we start off by looking for the average value in our data set. So here again, we have a histogram over some data. These are the cell counts with these particular values. So find the average value, and that happens to be there, and then calculate a standard deviation. What's the standard deviation of our data? And then we can plot the average minus 1 standard deviation, the average plus 1 standard deviation, or 2 standard deviations. So this is how we can then stretch our data out between these standard deviations. And what this means is that we can get rid of some extreme values. For example, in this data set here, perhaps these aren't terribly useful. There are only a few cells in each value. They're particularly bright cells somewhere. Maybe that's not where things are happening. Maybe that's not what we're particularly interested in seeing. Maybe we should be focusing more on this area here. So maybe you want half a standard deviation, 1 standard deviation, 1.5, 2, something like that. Adjust the number of standard deviations and you might get a better stretch of the data. But it's going to be dependent on what the histogram looks like. And then your assessment of the image, how do you think you can see more in it? Similarly with the Gaussian stretch, or Gaussian, sorry, not Gauss, Gaussian stretch, the Gaussian stretch uses the standard Gaussian function, which is this thing here. This applies, this is the same function you will find in statistics in so many different places. This describes this curve here. And we have, here we have the average value. Again, we've worked out the average. This is actually the same curve as before. The histogram that we saw before is now plotted as this black line here. So here we have the mean, and then we have 1 standard deviation below and 1 above there. It's the same, those same statistics have been worked out, but we then apply them to this formula. This tells us there's a function x given that we have this particular mean and this particular standard deviation. And so for each value of x, we can then recalculate it. We put x into it. So whichever value we're picking up from the black line here, we put that into our equation there, and that will give us a new value that then puts us, in this case, puts us down to that blue line there. Great. So that's the Gaussian stretch using this thing here. And as you can see, I mean, this looks complicated, but all this is the current value that you're interested in calculating minus the average. That's the standard deviation down there. That's Euler's number there. And that's again the standard deviation. That's pi. That's just the square root of the product of all of those. So actually, when you break it down bit by bit, it's actually quite easy. So that's you're taking this and then multiplying it by Euler's number, which has been raised to this bit, the negative of that bit there. So it's actually not that difficult when you break it down bit by bit. And you can create this nice Gaussian curve, the bell curve. And as you can see, somehow pi and Euler get in there. They get in everywhere. So that's how that stretch works. Typically, one of the problems we can see here, I said I'd point out some of the problems, typically with the Gaussian stretch, we're setting this C value, or with the number of standard deviations, we're setting to 3. And, well, that's not going to work in the case of this data. So you might have to adjust that to 1, whatever. Maybe the Gaussian stretch isn't appropriate in this case for this data. Maybe you'd have to choose a different stretch. It's not going to always be correct. Another type of stretch, the gamma stretch, fairly basic, where the new value of x, the function that we're looking at is this one, and it says x given this particular k and this particular gamma, hence the gamma stretch. So this is k is normally set to 1, so normally it doesn't really need to be there because 1's just not going to do anything there. It doesn't have to be set to 1, but it could be. And then gamma is typically set to something less than 1. So you end up stretching the values by raising them to a power of something slightly less than 1. And this will increase the contrast, hopefully. This sometimes gives you a good image to analyze, sometimes not. Okay, the choice, you're going to have to experiment, see which one gives you the best enhancement.